This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we'll be delving into a research paper titled Cognitive Guardrails for Open World Decision-Making in Autonomous Drone Swarms. This paper presents the Cairn framework designed to guide autonomous decision-making in dynamic and uncertain environments, specifically focusing on search and rescue missions using drone swarms. Let's start with the core challenge addressed by this research. What are the limitations of traditional computer vision systems in open-world scenarios, and how does the paper propose to overcome them?
Traditional computer vision systems often struggle in open-world environments because they're typically closed-world systems. They're trained on specific objects and lack the ability to handle unfamiliar objects or situations. This paper addresses this by integrating large language models, LLMs, to reason about detected objects and their relevance to the mission. The key innovation is the incorporation of cognitive guardrails to mitigate the risks associated with LLM hallucinations and inaccuracies, ensuring safe and reliable decision-making.
The use of LLMs introduces a new set of challenges. Can you elaborate on the potential pitfalls of relying on LLMs for decision-making in this context, and how the cognitive guardrails address these issues?
LLMs, while powerful, are prone to hallucinations generating incorrect or nonsensical outputs. In a search and rescue scenario, an incorrect LLM recommendation could have serious consequences. The cognitive guardrails are a multi-layered approach to mitigate this risk. They include things like format validation of LLM outputs, contextual grounding through retrieval-augmented generation, RAG, and runtime checks for ethical, safety, and regulatory compliance.
The paper mentions a Bayesian model for contextual reasoning and planning. How does this model work in conjunction with the LM, and what role does it play in the overall decision-making process?
The Bayesian model provides a probabilistic framework for reasoning about search strategies. It incorporates environmental conditions, lost person profiles, and evidence gathered by the drones. The LLM helps interpret the evidence, assigning relevance and confidence scores to detected clues. The Bayesian model then updates its belief about the optimal search strategy based on this information, guiding the drone swarm's actions. This interplay allows for dynamic adaptation to evolving situations.
The paper details a multi-stage LLM pipeline. Can you walk us through the key stages and interactions, highlighting the role of RAG and the knowledge base?
The pipeline begins with computer vision detecting potential clues. These are then analyzed by the visual LLM, providing labels and descriptions. RAG, retrieval-augmented generation, plays a crucial role by retrieving relevant information from a curated knowledge base of SAR best practices. This contextual information enriches the LLM's reasoning process. Subsequent stages assess clue relevance, infer tactical implications, generate strategic plans, and check for ethical, safety, and regulatory concerns. Finally, it determines whether human intervention is needed before executing the plan.
Let's delve deeper into the cognitive guardrails. You mentioned several types. Can you explain the decision time guardrails in more detail, focusing on belief entropy and cost-benefit analysis?
Decision time guardrails are implemented before any action is taken. Belief entropy measures the uncertainty in the Bayesian model's belief distribution over search strategies. Low entropy allows for autonomous action within the dominant strategy, while high entropy requires human confirmation for strategy changes. Cost-benefit analysis weighs the expected value of an action against its cost, preventing the drones from pursuing low-value or risky actions without human approval.
Beyond decision time guardrails, the paper also discusses a safety envelope and dual-phase human oversight. How do these mechanisms contribute to the overall safety and reliability of the system?
The safety envelope defines hard operational limits that the drones cannot violate, regardless of the LLM's recommendations. This provides a crucial safety net. Dual-phase human oversight involves human consultation during decision-making for uncertain or risky actions, and continuous runtime monitoring to maintain situational awareness and intervene if necessary. This combination ensures accountability and prevents catastrophic failures.
The paper mentions the use of runtime advocates. What are these, and how do they enhance the safety and ethical considerations of the system?
Runtime advocates are independent LLM-based agents that check for regulatory, ethical, and safety concerns. They act as expert advisors, drawing from various standards and guidelines. For example, a safety advocate might assess potential hazards, while an ethical advocate considers broader ethical implications. This multi-perspective evaluation helps identify and mitigate potential risks before actions are taken.
The paper describes both simulation and real-world validation efforts. Can you summarize the key findings from the simulation environment and the plans for real-world deployment?
The simulation environment validated the core functionality of Cairn, demonstrating its ability to handle diverse scenarios and adapt to new information. Real-world deployment is planned using the drone response platform, integrating the Cairn framework onto custom-built drones equipped with powerful AI processing capabilities. This will allow for testing in realistic search and rescue scenarios.
What are the limitations of the current CAN framework and what areas are identified for future research and development?
Current limitations include the manual definition of some parameters in the Bayesian model and the need for further refinement of the LLM prompts and knowledge base. Future work will involve broader evaluation across diverse missions, comparison with traditional search methods, and extensive real-world testing. Expanding the applicability of CARN to other domains beyond search and rescue is also a key goal.
The paper highlights the potential of CAN for various applications beyond search and rescue. Can you elaborate on some of these potential applications and how the framework's adaptability makes it suitable for these diverse contexts?
CARN's adaptability stems from its ability to handle open-world situations and learn from new data. This makes it suitable for applications like solar farm inspections, where drones need to identify anomalies, or wildfire management, where real-time adaptation to changing conditions is crucial. In essence, any scenario requiring autonomous decision-making in uncertain environments could benefit from CAN's capabilities.
The paper mentions participatory design with SAR experts. How does this approach contribute to the framework's effectiveness and real-world applicability?
Participatory design ensures that the framework aligns with the needs and expectations of real-world SAR practitioners. It allows for iterative feedback and refinement, ensuring that the system's decisions are not only technically sound but also practically useful and acceptable to the end users. This collaborative approach is crucial for successful technology transfer and adoption.
Considering the complexity of the CAN framework, what are the key challenges in terms of implementation and deployment, and how are these being addressed?
Key challenges include the computational demands of the LLM pipeline and the need for robust communication and coordination within the drone swarm. These are being addressed through the use of powerful edge computing devices on the drones and a robust communication infrastructure. Furthermore, the modular design of CAN allows for incremental deployment and testing, mitigating risks associated with large-scale system integration.
Finally, what is the overall significance of the caring framework in the context of autonomous systems and human-machine teaming?
CARN represents a significant advancement in enabling principled autonomy in complex, open-world environments. It demonstrates how LLMs can be safely and effectively integrated into autonomous systems, enhancing their capabilities while mitigating risks. The framework's emphasis on human-machine teaming ensures that humans remain in the loop, providing oversight and accountability, leading to more reliable and trustworthy autonomous systems. This is a crucial step towards the development of robust and responsible AI for real-world applications.
Thank you for this insightful discussion.